How can we systematically solve first-order linear differential equations? I'm Matthew Wright at St. Olaf College, and I would like to present a method for solving such equations in this video. We know that we can solve a differential equation of the form dy dx equals f of x by integrating both sides, assuming that we can evaluate the integral of f of x. However, suppose that we want to solve the differential equation x times dy dx plus y equals x. Now the left side is not simply dy dx, but something a bit more complicated. Can we solve by integrating both sides? Yes, if we realize that the left side is the derivative of the product x times y. Recalling the product rule from calculus, we see that this differential equation is really the derivative with respect to x of the product x times y equals x. Now we can integrate both sides, and we find that xy equals 1/2 x squared plus c. Dividing by x, we find that the general solution is y of x equals 1/2 x plus c over x. The previous example suggests a general method for solving first-order linear differential equations, that is, equations of the form dy dt plus g of t times y equals b of t. We would like the left side to be the derivative of a product of y and some function of t. This might not automatically be the case, but we can turn the left side into such a product by multiplying by a certain function. Let this function be mu of t. We don't yet know what mu of t is, but let's assume that it exists. We will multiply both sides of the differential equation by mu of t, and then figure out what this function must be. We want the left side to be the derivative of the product of mu of t and y. Don't forget that mu and y are really functions of t, even though we don't always write the t. By the product rule, the derivative of mu times y is mu times dy dt plus d mu dt times y. Matching up the terms in the product rule with those in the differential equation, we see that we want d mu dt to equal mu times g. But now we have a separable differential equation that we can solve for mu. Separating variables, we find that d mu over mu equals g of t dt. We integrate both sides and find that the natural log of mu of t equals an antiderivative of g of t. Solving for mu, we find that mu of t equals e to the antiderivative of g of t. This is a family of functions depending on the constant c, but we only need one such function, so we will choose c to be 0. Thus, we have found our function mu of t. This function is called the integrating factor. Our original differential equation can now be written as follows. The derivative of the product of mu and y equals mu of t times b of t. Integrating both sides, we find that mu times y equals the integral of mu times b. Dividing now by mu, we obtain our solution y of t. Y of t equals 1 over mu of t times the integral of mu of t times b of t. Thus, we have an explicit formula for the solution as long as we can evaluate two integrals, the integral that defines mu of t and the integral of mu times b. Let's look at a few examples. First, dy dt plus 4ty equals 2t. We see that this differential equation is in the proper form. G of t equals 4t and b of t equals 2t. We find the integrating factor. G of t equals 4t, so mu of t equals e to the integral of 4t dt, which is e to the 2t squared. We multiply both sides of the differential equation by e to the 2t squared. Check to see that the left side really is the derivative of e to the 2t squared times y. You might want to pause the video and check this using the product rule. Okay, now we can integrate both sides, and we obtain e to the 2t squared times y equals the integral of 2t e to the 2t squared. Applying the substitution u equals 2t squared, we compute the integral, 1/2 e to the 2t squared plus c. Solving for y, we find that y of t equals 1/2 plus c times e to the negative 2t squared. This is the general solution to the differential equation. You should check this solution by computing its derivative and substituting back into the differential equation. For another example, consider dy dt plus 4ty equals 2. Notice that this differential equation is nearly the same as in our last example, but now the right side is just 2 rather than 2t. We compute the integrating factor and find that mu of t equals e to the 2t squared as before. Multiply both sides of the differential equation by mu and check that the left side is the derivative of a product. Specifically, we have the derivative of e to the 2t squared times y on the left and 2e to the 2t squared on the right. We now integrate both sides. Unfortunately, we find that the right side is the integral of 2e to the 2t squared. You might remember from calculus class that the integral of e to the t squared cannot be simplified in terms of elementary functions, so there isn't much we can do with this integral. However, we can still write the solution y of t as y of t equals 2e to the negative 2t squared times the integral of e to the 2t squared dt. This still defines a function that solves the differential equation, even though the formula for y of t contains an integral. We can still approximate this function numerically, but we can't simplify any further algebraically. Let's summarize the steps of the integrating factor method. To solve a first-order linear differential equation. First, if necessary, rearrange the differential equation to put it in the form dy dt plus g of t times y equals b of t. Second, compute the integrating factor mu of t equals e to the integral of g of t dt. Multiply the differential equation by mu of t and check that the left side really is the derivative of mu times y. Third, integrate both sides and divide by mu of t to obtain y of t. Now you have found the solution, but you should check that y of t really does satisfy the differential equation. Note that you can and should check your work at steps 2 and 3. This will help you avoid mistakes in your answer. We will end with one more example. Consider the differential equation 2t dy dt plus y equals 4t squared plus 3t for t greater than 0. Furthermore, suppose that we have an initial condition y of 1 equals 2, so this is an initial value problem. To solve the problem, we must rearrange the equation to put it in the form dy dt plus y over 2t equals 2t plus 3 halves. Now we see that g of t equals 1 over 2t. So the integrating factor is mu of t equals e to the integral of 1 over 2t dt, which is e to the 1/2 natural log of t. Since t is greater than 0, we don't need an absolute value in the natural log. Simplifying, we find that mu of t equals the square root of t. Multiplying both sides of the differential equation by mu, we check that we have the derivative of a product on the left. We see that the left side is the derivative of y times the square root of t, so we know that we are correct up to here. The right side is 2t to the 3 halves plus 3 halves t to the 1/2. Now we integrate both sides. Y times the square root of t equals the integral of the right side, which is 4/5 t to the 5 halves plus t to the 3 halves plus c. Dividing by the square root of t, we find the general solution. Y of t equals 4/5 t squared plus t plus c over root t. We are almost done, but recall that this problem has an initial condition, y of 1 equals 2. Substituting 1 for t in the general solution, we find that y of 1 equals 4/5 plus 1 plus c. All of this is supposed to equal 2, so c must be 1/5. Thus, the particular solution is y of t equals 4/5 t squared plus t plus 1 over 5 root t. You should differentiate and check to verify that this does in fact solve the differential equation.